There we go. Recording is started. So today we're going to cover, actually, let me go back to fifth lecture. Here we go. So here we've got, we're on lecture 5 of the first section of the class where we'll be talking about just kind of the basics. So last section and this section, we're talking about the 5 dead white guys. We're going to talk briefly about Galileo, which we missed last time, and then we'll be talking about Kepler and Brahe today. So a little bit finishing up in lecture 4, we've got lecture 5 there. And then we've got an exam coming up on February 16th. This is the intro part, then we've got the stars part, and then the galaxy part. So let's go back to Galileo. Here are the 5 dead white guys. Copernicus, who was the first one to say that maybe we were not the center of everything. In fact, there's the Copernican hypothesis that we are nothing special. Then we've got 3 people that were all alive at the same time: Galileo, Brahe, and Kepler. We're going to cover all of those today, and then Newton will be covering in a future lecture. So let's see. Goes there, that goes there. Oops. Resumes here. Why does it do that? There we go. So here's Galileo Galilei. He lived, well, in the early 1600s. He did not invent the telescopes. Are these slides on WebAssign? Yes, they are. So, in fact, I think I already posted them. Hopefully blast off soon, yes. He did not invent the telescope. The telescope had been around for several years. They called it a spyglass, but he was the first one to really use it for astronomical observations. He did use it to confirm the Copernican model. By the way, there's 2 sets of slides on WebAssign under resources. There's the slides that are available from the publisher, and then there's my slides, and they're separate. Take your choice which one you get. Since the exams are done solely off of the textbook, you would have nothing to lose by just looking at the slides from the textbook. And when he observed the sky, he observed the sky that did not look anything like the Ptolemaic geocentric universe. What he saw was a confirmation of the Copernican model. So he was really what we would call the first modern scientist, that he used observations to create hypotheses and theories, and those observations he would either confirm or deny that theory. Unlike previous scientists or philosophers, as they called them then, who really were just trying to validate their preconceived notions based on the ancient text. Where's resources and WebAssign again? You just have to scroll down, okay? So you've got the assignments. If you keep scrolling, you'll see resources at the bottom. And he stood up to the Vatican. The story is much more complicated than I'm presenting here because I've only got a couple of slides at Copernicus. I'd recommend you read a book about Galileo. He wasn't a bomb thrower. He had friends in the Vatican and high places. The problem was that one of his great friends in the Vatican died and left him exposed. And well, anyway, it's a long story. But Galileo was a really great guy, the first modern scientist. One of the things he observed was the moon. He noticed that the moon had mountains and craters, and the moon was nothing like the pure world that the Vatican was saying that it was. He also observed the Saturns of Jupiter. We now call them the Galilean satellites. There's 4 satellites that are so big that he could observe them even with the tiny little silly telescope that he had at the time. You can definitely observe them with binoculars, which are actually a little bit better than the telescope he was using. And here is a record of his observations, proving that these Galilean satellites actually orbited Jupiter, that not everything orbited the Earth. that things orbited other bodies. He also observed, and here's a very low resolution picture of Jupiter and the Galilean satellites. Again, you can see these with just a pair of binoculars. He also looked at the orbit of Venus, Venus's phases. And why are Venus's phases a big deal? Because this was absolute proof that the geocentric model could not work. And I'll show you why in a minute. So in the Ptolemaic universe, or the geocentric universe, the Venus, everything orbited the Earth, the sun orbits the Earth, Venus orbits the Earth, but as it orbits the Earth, it also goes around this epicycle. The way that they designed this epicycle, Venus was never full. There was always a partial Venus. You couldn't notice this visually because your eye isn't sensitive enough to resolve any sort of features on Venus. In the Copernican universe, where everything revolves around the sun, not the Earth, you would be able to see all of the phases of Venus. And only Galileo with the telescope could actually observe these phases of Venus. You can't do it with the naked eye. And let me bring up a couple of simulations to show you that. So, new share. Okay. So here is, here's the Earth. Earth is the center of the universe in the Ptolemaic version, or the geocentric version. Those are synonyms. There is the sun, and here is Venus going on its epicycles, okay? And this matches the observations very precisely, that Venus has to be, never gets too far away from the sun as the sun goes around the Earth, at least in this model. And you can see by here, the part of Venus that's exposed to the sun is shown there. And this is what it would look like if you had a telescope on Earth. It would get bigger and it gets smaller. And there's always a crescent, and the crescent gets bigger and smaller, but it never becomes full. Okay. Whereas in the heliocentric version of the universe, where Venus and Earth both orbit the sun, okay? And again, both of these models are predictive in terms of where Venus is on the sky. But notice here, there are times when Venus is completely opposite us from the sun, and the entire circle of Venus is exposed, and so it's got a full phase. And so this is absolute proof that the geocentric universe does not work. Now, what scientists at the time said was they didn't believe their lying eyes, literally. They didn't believe what they saw. So the history of denying evidence goes way back. It's not just a symptom of today's problems, but it goes way back. Okay. So let's go back to that lecture. And that's it. Okay, so that's the end of chapter 4, or lecture 4. Let's go on to lecture 5. Where is lecture 5? Shoot. Okay. There's lecture 5. Lecture 5. Geez, come on. Okay. Lecture 5. So what we're going to cover some random issues here. Solar versus sidereal days. We're going to cover angular measurements. We're going to cover orbits, and then Kepler's laws. So today we're covering Brahe and Kepler when we get to Kepler's laws, and then we're covering just some other topics that we need as we move forward in this class. Solar versus sidereal days. This is just pretty much a definition, but it's really confusing. So I'm going to go over this fairly slow. It might seem simple, but it's confusing. Even I get confused about this. So, oh, by the way, we talked about how we are made of stardust. Here is absolute proof of that fact. This is a new photograph of a new planetary nebula in the Orion constellation, and you can see it does prove that we are stardust. Okay. So, question for you, and please put your answer in the chat. What do you think defines a day? What is a day? So no God? We're not studying that today. No, so 24 hours isn't really fair because 24 hours is the way we have split up the day. So the question is, if you didn't have hours, you didn't have a watch, how would you define one day versus the next day? A full planetary rotation. That's correct. Sunrise to sunset. So you say one rotation of the Earth's axis, but one rotation of the Earth's axis from what to what? In other words, as the Earth goes around, what are you measuring that rotation with respect to? Okay. So I see a bunch of sunrises. The sun, right. Okay. So the way traditionally the day has been defined is from sun to sun. Okay. So, and actually using sunset and sunrise would be a really bad idea. And the reason why is that sunrise and sunset vary over the entire year. The one thing you could do is noon. Okay. Noon is where the sun is directly as high overhead as it's possibly going to get during that day. And so as sundial would actually measure that day, and that's called a solar day. You're measuring it from sun to sun. Okay. Time is infinite. Time is illusion. That's cute. Time is a lie anyways. So Tavia, yeah, time is really what we need to keep everything from happening all at once. Okay, so that's why time was invented. Time is a human construct. Andrew, philosophers have made that argument, but it's not true. It's not true because time continues to march forward independent of our existence. You know, I think that most people would believe that if all humans disappeared instantly, time would still keep on going, minding its own business. Anyway, so where we're back to days. Days are measured sun to sun. That's wrong. Okay. That's wrong because, well, it's not actually wrong. I'm misstating it. It's not complete. It's not complete because the sun moves relative to the universe, at least from our observation. Okay. So as we go from sun to sun, the day that we measure is actually longer than the true day. And the true day is called a sidereal day. And the sidereal day is why measuring not sun to sun, but from sky to sky. In other words, I measure the rotation relative to the fixed universe. Okay. And that's called the sidereal day. And they're different. So the sidereal day is about 23 hours and 56 minutes. So let me bring up a couple of simulations to show this better. Okay. Share. Yeah, I don't like that one. Let's try the other one. Okay. So here's the sun. Here is the Earth. We go one solar day. Okay. And note that as we went around, that angle is like this. Whereas if we did one sidereal day, notice that we're pointing in the same direction relative to the fixed sky, okay, which is over here someplace. And so the sidereal day is always shorter than the solar day because the solar day, you have to go a little bit farther to get back to the sun. And the difference is 4 minutes a day. Okay, it's 23 hours, 56 minutes. So the question for you is, let's assume this isn't true, but let's assume that there's 365 solar days in a year. How many sidereal days are there in a year? Uh, so John, that's correct. If you notice here, this simulation is saying that the length of the day is 240 hours. That's just so we can see this. If I said at 24 hours, the change from day to day, you wouldn't be able to see. So the question for all of you, and put your answer in the chat, is if the number of solar days, sun to sun, is 365 days, how many sidereal days would there be in a year? 366, that's correct. Because the sidereal days are a little bit shorter. So you can fit more of those into the year. Okay. So I know that's confusing, but it's important that you always, when you make a measurement, you got to know what is the measurement relative to. Okay. So let's go back. Solar day is sun to sun. Sidereal day is star to star. Is that why we need leap years, Travis? No, it's not. The reason we need leap years is that we define the day based on the rotation of the Earth. The Earth rotates around. We define the year by the revolution of, do I have that? I always get revolve and rotate mixed up, sorry. We have the sun, the Earth going around the sun, and that takes 365.2524 days, okay? And there's no reason why one needs to be divisible by another, and they're not, okay? And that's why there's little left over. That the rotation of the Earth and the movement of the Earth in orbit around the sun don't have to be divisible by each other. So an interesting fact, the fact that it was 365.25 was known to the ancients. So this was the basis of what we call the Julian calendar after Julius Caesar, that every 4 years, the Romans would add an extra day to make up for that. What they didn't make up for was it's not 0.25, it's 0.2524. And that extra little 0.0024 over 1500 years added up. So by the time you get to the 1600s, the calendar was off by about 14 days. And so that's why there was this big shift in the medieval times from the Julian to the Gregorian calendar. And that's why sometimes looking at dates during the medieval times is really fraught with peril, because different countries switched over to the modern calendar that we use today at different times. And the Gregorian, the new calendar has leap days not only every 4 years, but every 100 years, except 100 years that are divisible by 400. Okay, long story. In saying that the Romans were able to figure that, yeah, we continually forget that the ancients were just as smart as we were. They just didn't have the tools we were. And the fact they could figure it out was amazing. Does general relativity impact the way we perceive time at all? Absolutely, Christine. And we'll be covering that in 2 or 3 lectures in a little bit. So yes, general relativity definitely does affect the way we perceive time. Okay, so enough of sidereal and whatnot. Let's go to angular measurements, which I know is on the homework. This should be review. We covered this the first lecture. There's 360 degrees in a circle. There's 60 arc minutes in a degree, 60 arc seconds in a degree, in an arc minute. So there's 3,600 arc seconds in a degree. Your thumb is about a degree, depending on the size of your thumb. So the moon and the sun is about half your thumb. Your eye can perceive objects that are separated by about an arc minute. And since the moon and the sun are about 30 arc minutes across, that means that we can see some detail on the moon, even with the naked eye. Best telescope, most telescopes on the surface of the Earth have about an arc second resolution. Arc second, best telescope resolution, arc minute, your naked eye resolution, half a degree, the size of the sun and the moon. Okay. So here are pictures of the planets. I think that's, oh, it's labeled right there: Venus, Mars, Jupiter, Saturn at various dates. Notice that Jupiter and Saturn don't change a lot in terms of the perceived size on Earth. That's just because they're so far away. So the difference in the Earth being a little closer and a little farther away doesn't matter. But notice that Mars changes significantly in size as it goes around the orbit, as does Venus. Okay, just because they're relatively close to the Earth. And so here is 10 arc seconds. Okay, so this is much greater than you can see with the naked eye. And so here, a basic ground-based telescope is going to have about the same resolution on Jupiter as the naked eye has on the moon. The moon has about 30 arc minutes across, so you can see about 30 things. Here, a telescope has about 30 arc seconds across on Jupiter, and so you can see about 30 things on Jupiter. Okay. So the question is, can you get what the angular diameter should be? In other words, how many arc seconds or arc minutes it should be, and use that to calculate either how far away it is or how big it is? And the answer is yes, as you found out in the homework. But to get there, we have to give you some, what telescope did you, I didn't take that picture. The problem is that all ground-based telescopes except really advanced telescopes are limited to about an arc second resolution because of the atmosphere. Only really advanced professional telescopes that have computers that warp the mirror can get better than 1 arc second. It's kind of weird because my little 4-inch telescope has the same resolution as a big, 100-inch telescope. So before we get to measuring, using angular diameters to figure out distances, or conversely, using distances to figure out the real size of things, we need to review trigonometry, which every single one of you have had. If you didn't have it, you wouldn't be in this course. It is a prerequisite for this course. So refresh your memory. Here's a triangle, a right triangle. We've got X, we've got Y, and you got the hypotenuse. I call the side adjacent to the angle, the adjacent side, the side opposite the angle, the opposite, and then the hypotenuse is the long thing on the top. Okay. And so to memorize where the sine and the cosine and the tan goes, there's these mnemonics, SOH, CAH, and TOA. SOH means sine is equal to the opposite over the hypotenuse. So y over hypotenuse is the sine. The cosine is equal to the adjacent over the hypotenuse, so the adjacent over the hypotenuse. And the tangent is equal to the opposite over adjacent. So, ka, ta, okay? So just memorize that, okay? Or you should already know this if you're in this class. Just knowing what sine, cosine, tan is going to be so valuable. I mean, as you're walking down the street, it's going to be very valuable as you observe things, okay? You'll need these skills, trust me. So another way of expressing the tangent is the tangent of the angle is y over x, or opposite over adjacent. Y is the vertical side here, x is the horizontal side. Okay. So, and from now on and throughout this entire course, actually we're going to be using both. We use angles, the 360 degrees. We also use radians. And so it's a little confusing, but you need to know both. Just know that when I say radians, 2 pi radians is 1 circle. So 2 pi radians is equal to 360 degrees. And this course, unfortunately, we use both measurements. If I measure the angle in radians, there is the tangent of the angle in radians. There is the sine of the angle in radians. And so for small angles, the tangent of the angle and the sine of the angle are the same, which isn't surprising because the tangent is opposite over adjacent and the sine is opposite over hypotenuse. And for small angles, the hypotenuse and the adjacent are approximately the same, okay? So this isn't surprising. What is surprising, will the measurement unit be stated on the exam? Absolutely. And remember, yes, I will be very clear when we're using radians and when we're using angles. What is surprising is the fact that if I write down just the angle compared to the tangent of the angle and the sine of the angle, for small angles, the sine of the angle, the tangent of the angle, and the angle itself are all approximately the same. So the small angle approximation is here. Tangent of the angle is approximately equal to sine of the angle is approximately equal to the angle. Again, all in radians for small angles, okay? So the tangent of the angle is equal to y over x is approximately equal to sine of the angle is approximately equal to the angle. Why do we care about this? We care about this because in astronomy, all angles are small. If you got a big angle, that asteroid's going to hit you in the next 30 milliseconds and you're dead. So all angles are small. So that's why we always use the small angle formula in astronomy. And so here you are, okay, and you're looking at a planetary object. You note the angular diameter. You see how big it is on your retina. And that angular diameter is equal to the linear diameter over the distance. So if you know how big the object is, you can calculate how far away it is. If you know how far away it is, you can calculate what the linear diameter is. So the small angle formula is a relationship between three things: the linear diameter, the size of the object, the distance of the object, and the angular diameter of the object, how big it appears. And typically you observe the angular diameter and you derive one of these other two, depending on which one you know. Okay. And here is the formula we use in this course. The angular diameter, and again, we're just switching units here. Sorry about that. In arc seconds, and that's that double thing there, over this number, 206,265, is equal to the linear diameter over distance. So this is kind of a cheat sheet. This is a formula. I will expect you to know the formula. If it's on a test, I'll give you this number here, the 206,000. So you won't have to memorize this number, but certainly know that the angular diameter is, for small angles, equal to the linear diameter over the distance, okay? So, or this is the linear diameter over the distance is the tangent of the angle, which is approximately equal to the angle, which is approximately equal just to that ratio, okay? And this value here, 206,265, just makes it very convenient to do your calculations in terms of arc seconds. Where does the 206,265 come from? That number comes from a units conversion. So you're converting from radians to arc seconds. And remember, 1 arc second is 3,600 degrees. So because if this was in radians, so you could say that this in radians is equal to linear diameter over distance. And so we just convert radians into arc seconds, and that's where that number comes from. Okay. So if we know the distance to Jupiter, then we know the diameter of Jupiter, and we know the angular diameter. So if we know the angular diameter and the distance, then we can calculate how big Jupiter is. Will the angular diameter be given in arc seconds, or will we have to convert it? So I don't like to do a lot of conversions in the exams. So I will tell you if you need, I'll tell you if you need to have it in arc seconds, and I will, if you need it in arc seconds, I will give you that value, the 265,000. Okay. So that's it. That's the small angle formula. I went over it fairly slow because it's a simple formula, but it can get really confusing. And that's the justification for it. Okay. And the thing about the small angle formula is that objects that are very different in size can have the same angular diameter, because the ratio of the linear diameter to the distance is the same. Okay. So here is another example. So here we've got, and so here's an example. Here's 3.4 by 10 of, anyway, you can read those numbers there, sorry. And here is two numbers for the linear diameter and distance for a larger object. And those two are exactly the same, because those two will wind up with the same arc seconds. Okay. So the small angle formula always has, so BB, the small angle formula has that constant if the answer is in arc seconds. Now you can leave that off and you'll get the answer in radians, and then you can convert to arc seconds yourself by multiplying and dividing by 2 pi and 360 and 3600. I forget which number is which. So what the 206,000 does for you is it does the units conversions from radians to arc seconds for you. That's all it does. It's just a units conversion. Okay, so here's the example that the ratio of the linear diameter over the distance for two objects is approximately the same, so they both have the same angular diameter. Okay. So enough about angular measurements. Now let's talk about orbits. There's an art to flying, or rather a knack. The knack lies in learning how to throw yourself at the ground and miss, okay? Which is exactly what an orbit is, okay? So here you are again, and you're going to throw something. And yes, it's so sad that he's no longer with us. Anyway, you throw something and the ball um, curves down, hits the ground. What happens if you throw something harder? Throw something harder and it goes farther. What happens if you throw something really hard? It goes even farther. Okay. Yeah, I love Doug Adams. The movie wasn't that good, but his books are great. So here is the, the harder you throw something, the farther away it is from you. That's on a flat Earth. But remember, the Earth isn't flat. So what would happen if you do this on the real Earth? Okay. So here you're up on a mountaintop and you throw something a little bit and it curves down and it hits the Earth. But notice in the process of it curving down to hit the Earth, it's being pulled by gravity towards the center of the Earth has kind of bent away from it. And so it actually goes a little farther than you would expect if the Earth was flat. If I throw it even harder, notice it goes a lot farther because the Earth is curving away from it. Okay. Oh, I haven't seen the TV adaptation. Doesn't depend the angle you throw it at. So, I'm sorry, I can't pronounce Dylan. Yes. So Dylan, sorry about the pronunciation of your name. It does depend on the angle we throw it. That would take us far afield. So for now, we're just going to throw it flat. Okay. You might notice that when rockets are launched from Cape Kennedy, they do this, they go straight up for a while, but then they do this weird maneuver. And anyway, they do that because what they want to do is they want to approximate this throwing flat. Okay. So what would happen if I threw it really hard? If I threw it really hard, it will continually fall, but as it continually falls, the Earth moves away from it. Okay. And remember that the object is always going to be attracted not straight down, but towards the center of the Earth at all points. And so an orbit is nothing but always falling. If there was no air resistance, that's correct. It would just circle the Earth forever. Okay. And the air resistance is why rockets go straight up at first, because the most efficient thing for rockets to do was for rockets to go flat like this and go in orbit. But of course they can't because air resistance would burn it up. Okay. Have anything we put in space had the wrong angle and got lost in space forever? So Josh, yes, a whole bunch of stuff. In fact, just recently in the news, the scientists were excited because they discovered that there was a new moon of the Earth, and it was out close to the orbit of the moon, our moon, and they thought it was just a really small asteroid until they did a spectral analysis of it, and that spectral analysis proved that it was actually a lost rocket stage that had come back to Earth after orbiting interplanetary space, and now it was circling the Earth again. So yeah, there are things that have gotten lost. So for this circular orbit, it is constant angular velocity, and it actually is constant speed too. The velocity itself moves, and we'll be talking about that in a minute. Okay, so being in orbit is just constantly falling and missing. Okay, and the basic orbit is a circle, but it's not the only type of orbit. There's also the ellipse, as we talked about when we were talking about the Copernican things. We're going to talk more about ellipses in just a couple of minutes. Isn't there a bunch of space junk orbiting the Earth? Yes, Jacob. Oh my gosh, there's space junk. There's, I don't know, 10,000 things. There's a part of the Space Force, actually, weirdly, they didn't want to join the Space Force, but there's a group in the Cheyenne Mountain that does nothing but track all of the objects down that are orbiting the Earth down to the size of a quarter. Because if an object the size of the quarter hit the ISS, it could destroy it. Can it be harmful to have all that space junk out there, Sophia? Oh, absolutely. I would recommend you see the movie Gravity, which talks about that, and it's grossly over exaggerated, but the process is real. Low Earth orbit is dangerous because of all these things. The Chinese, for who knows why, they blew up a satellite on purpose in low Earth orbit, and there's thousands of those particles orbiting around and causing great chaos. Yeah, the science in Gravity was, how do we put this politely? Laughable. The concept of this being this cascade is certainly something that we're deeply worried about. But the way they showed the cascade isn't. I mean, they showed the objects hitting you every 90 minutes as they come by at a speed that looks like a few hundred miles an hour. In reality, it would hit you not at all, or it would just blast you at 17,000 miles an hour. And at that speed, you would not be able to see it. So, uh, how much quantity of space junk do they find so far? I think it's tens of thousands. Yeah. So anyway, so we have an ellipse. So if you throw a little harder, you get this elliptical orbit. And then a hyperbola is an orbit that actually never comes back. Okay. And these are all conic sections. We won't talk about that again. For those of you that love mathematics, circles, ellipses, parabolas, hyperbolas are all conic sections. It just has to do with the mathematics, which we won't really cover when we talk about Newton. How do they keep this stuff from hitting the ISS? Interesting question. They don't. And so the ISS actually has a shielding in the direction that it orbits to protect it from these particles. And anytime that there is a particle that they think is on an intercept orbit, they move the ISS. That's why the ISS has thrusters on it. And it is a big deal. And they have to do it, a couple times a month, I think. I don't know the exact number, but it's a big deal when they have to move it. And so they could withstand impacts from things as big as, a grain of sand, for example, but probably not much bigger than that. So if you went to the Air and Space Museum before it closed, they have a shuttle window. And the shuttle windows are several inches thick. They're like this. And the shuttle window had a crater on it. And the crater was about the size of my thumb. And it's the size of my thumb, but the shuttle window was so thick, it didn't quite penetrate the entire shuttle window. Okay. That crater was caused by an impact with an object in space that was orbiting. When that object hit the shuttle window, it made a noise so loud that all the astronauts heard it. It was a loud kerkump. And when it came back down from orbit, they discovered that the thing that created that crater, the size of my thumb, was a speck of paint that was microscopic. So, yeah, it's a real challenge. You would think they have lots of protection. Yeah, so they have protection, but, again, anything the size of a quarter, an impact with something the size of a quarter would wipe out the ISS. And luckily, that's the size that they can track. So here is Uma. This was an asteroid discovered 2-3 years ago. And what's unusual about Baba is that it wasn't on an elliptical orbit around the sun. It was on a hyperbolic orbit around the sun, which meant that it wasn't actually on an orbit, which meant that it had nothing to do with the sun. It was coming from interstellar space. This was the first one that we had discovered coming from interstellar space. We've since discovered, I think, 2 more. So why did they name it that? I don't know. Why don't you Google it and let me know? If that's a test question, I'm done. Okay. Yeah, I'm not going to, I will definitely not ask you what the name is. I will ask you, how did they know why the comet was interstellar? And the answer is it's on a hyperbolic orbit. Seems Hawaiian. Yeah, I think that's the answer, but I can't say for sure. Okay, orbits. We'll be getting back to orbits throughout this entire course, but we're going to leave it for now and going into Kepler's laws. Here are Kepler's laws. We're going to go over the laws in excruciating detail in a couple of minutes. There's Newton's three laws, which we'll be covering in a future lecture. And then we have Kepler's three laws, and you are responsible for these lectures. One is orbits are elliptical. 2, orbits sweep out equal areas in equal times. And 3, the square of the period equals the cube of the semi-major axis. P squared equals A cubed. Umu Amua. Umu Amua. Boy, that does sound very Hawaiian. Okay. My sister lived in Hawaii for 20 years. My mother lived there for years, where she met my father. Okay, anyway, it means first in Hawaiian. Oh, well, that makes sense because it is the first interstellar comet. So P squared equals A cubed is an equation you're responsible for. You will be doing very simple calculations for this. I'm not going to ask anything that you need a calculator for. And I'm not going to do anything complicated like elliptical orbits. All the orbits you'll be asked on are going to be nice and circular, except in the homework, I noticed they had one where you had to take the average of 2. Sorry about that. Angular diameter equals 265,000 times the diameter of a distance. Again, you need to know this equation. I promise I'll give you that number. So here are the 5 dead white guys. Today we're going to be talking, and just a few minutes ago we talked about Galileo. Now we're talking about Brahe and Kepler, 2 interesting guys. So Galileo, for scientists, Copernicus was, he published his heliocentric universe after he died. Galileo was the first scientist. Brahe considered the Paul Allen. He wasn't a scientist, he just had a lot of money. And so he funded a lot of stuff. And think of Kepler as Steve Wozniak. Kepler was this genius, brilliant guy that you kept in the closet, okay? And Brahe funded Kepler, and Kepler is the one that did the science. Brahe is the one who paid for all the science. And they're both equally famous because you need both of them to create the breakthrough in modern science that they created. Alternatively, Brahe is Elon Musk. Yes, that would also be a comparison. Okay. So here's Johannes Kepler, who was not terribly social. He worked with Tycho Brahe's data, and he was the one, after 20 years of work, discovered the 3 laws, which was amazing because, mathematics was not terribly sophisticated then. Remember, this is before calculus. He was just using very primitive mathematical tools. Also, this is really before the telescope. I mean, so Galileo was using a telescope, but Brahe's observatory did not use telescopes. And using this data, which was the most precise data at the time, pre-telescope, he found that the orbits were neither circular nor uniform. And you got to understand that the whole feeling for everybody at that time was the universe must be perfect because it's cosmic. So cosmos must be perfect. And so they were always looking for, one of the things that Kepler was looking for was, perfect objects like spheres and rhodahedrons and, perfect solids that would create the spacing of the orbits. And the fact that the orbits were not perfect, it took 20 years to figure that out. And it was not just trying to model it like we would today. It was like trying to break through 2,000 years of brainwashing to get to the fact that the universe actually isn't perfect. And he wrote the 3 laws of planetary motion, which are still true today. Now, you can derive these 3 laws from Newton's equations to prove basically these 3. We still use these 3 laws today. NASA uses the 3 laws, okay? Here's Brahe. That's what he looks like. So this is a picture of the young Brahe. I know it's a picture of the young Brahe. Can anybody tell me why that's a young Brahe? This little cute little quirk of Brahe will be on the exam. His nose isn't broken. That's correct. He actually had a golden nose because his original nose would cut off in a sword fight. Okay. Yeah. He was a very colorful character. So here is his observatory. It was huge by standards of the day. And he used very big instruments. And you can see how big this instrument is. So he get very precise measurements of locations in the night sky without telescopes. Yeah, he had a golden nose. Yeah. Goldfinger, except it wasn't Goldfinger, it was Gold Nose. Oh, I don't expect you to talk, Mr. Punt. I expect you to die. Yeah, right. Anyway, that was Brahe. And so Kepler worked in Brahe's observatory and was kind of a pet of Brahe for 20 years. Kepler's first law, the orbits of the planets are ellipses with the sun at one focus. Okay. And the semi-major axis is not the distance from the focus, the nearest approach, it's the distance from the center, which is why in the homework problem, you had to take the average of the nearest and farthest approach. So Kepler's first law. Yeah, so that's just, like I said, the equation is still precise. It still works today, as we'll discover when we go about Newton. Okay, so there's Kepler's first law, third law, p squared equals proportional to a cubed. And if you do period in year and distance in AU, then you can do calculations pretty easily. There's the third law. And let me show a simulation of that. Hold on. And Kepler. Okay. So someone asked, yes, the sun is at one of the foci of the ellipse. There's the radial lines. Here's Kepler's second law. And each of those is exactly the same area. And then third law shows that the relationship between p squared and a cubed follows this. Okay, let's reset everything. And let's show you, there are all the orbits for the solar system. This sample orbit is fairly elliptical. Notice that, so the eccentricity of Mercury is pretty big. The eccentricity for Mars isn't that bad. Okay, so every orbit is different. Okay. And wow. And you can see it's not terribly elliptical. In fact, I think Earth is even less elliptical. There we go. Yeah, see how close to circular the Earth's orbit is. Okay. Let's try Venus. Venus is almost perfectly circular. And let's try Mercury. Oh, Mercury is very elliptical compared to these other orbits. Okay. Do we know if the law holds up in other solar systems, or is there some kind of constant? So the p squared equals a cubed holds for the entire universe. The reason why is, although Kepler didn't know it, the p squared equals a cubed is derived from conservation of angular momentum and from Newton's laws of gravity. And those two, as far as we know, are absolute rules of our universe. Okay. So it's now 12:45. I had some questions, but I've run out of time. So